Integration of rational functions is done using an algebraic procedure known as partial fractions. Because the general procedure is rather complicated to explain, we'll introduce it by looking at successively more complicated examples. Let's start off with this kind of example where we have a linear function on the top and a quadratic function on the bottom. In particular, a product of two linear factors on the bottom. Let's look at a similar kind of problem that we know how to solve. The integral of 1 over x squared plus 1 is arctan x. Now notice this is not quite of this form because x squared plus 1 is irreducible. It doesn't have any real roots, we can't factor it. If we change this plus to minus, we get a different problem, 1 over x squared minus 1, that we can't solve using arctan or any similar approach. So let's see how we can solve it. And let me start by just pulling something out of my hat. So if we take 1 over x minus 1 minus 1 over x plus 1 and we put it over a common denominator, we get this algebraic calculation here. On the top we get x plus 1 minus x minus 1, which is 2. And on the bottom we get x minus 1 times x plus 1, which is x squared minus 1. So that tells us that 1 over x squared minus 1 is a half of the left-hand side, and we know how to integrate these two functions. They're just logs. So to summarize this, the integral of 1 over x squared minus 1 is 1 half the integral of 1 over x minus 1 minus 1 over x plus 1. And this is 1 half log absolute value x minus 1 minus log absolute value x plus 1 plus a constant. And we can rewrite it in this form if we want, using the laws of logs. So what does that tell us? That tells us if we can rewrite our function into this form as the sum of the reciprocals of linear functions, then we can easily solve our integration problem because we know the antiderivatives of these are just simple logs. And it turns out that there is an algebraic theorem that says we can always do this for these kind of functions. So let's look at a different example. Let's suppose we are looking at, we want to integrate 4x plus 1 over x squared minus x minus 2. Well, let's start off by noticing that the denominator really is a product of linear factors, because we can factorize this as x minus 2x plus 1. So what we do is we assume this theorem from algebra that this can be expressed as some constant over x minus 2 plus another constant over x plus 1. And we go ahead and solve to find out what a and b should be. To do this, we multiply by x minus 2, x plus 1, both sides of this equation, and then solve for a and b. So doing this cancels out the denominator on the left-hand side and gives us 4x plus 1. When we multiply a over x minus 2 by this product, the x minus 2's cancel out and we just get ax plus 1. And similarly, when we multiply b over x plus 1 by this product, we get b times x minus 2. Now, this is true for all values of x, so we can just pick some values of x, specific values of x for which this gives us an interesting result. So for instance, if we pick x equals 2, this term will become 0, and it'll give us an expression for a. On the left-hand side, we get 4 times 2 plus 1, which is 9. On the right-hand side, we get a times 2 plus 1, which is 3a, and 0 times b. So that tells us that a is equal to 3. And the way we chose our value for x was to make this term 0. To make this term 0, we should choose x to be equal to minus 1. So we go ahead and we substitute in x equals minus 1 into this. Now the a term disappears and we get minus 3b is equal to minus 3, so b is equal to 1. So Our algebraic procedure has given this identity, which we can check by doing the same process, putting the right-hand side over a common denominator and rewriting it, and we'll get the left-hand side. So now we can find our integral. It's the integral of 3 over x minus 2 plus 1 over x plus 1, and that's just 3x log x minus 2 plus log x plus 1. So this is the general method. Whenever we have a rational function of this form, a linear function over the product of two linear functions like this, we can write it as a over x minus alpha plus b over x minus beta, and repeat that kind of process to find the specific values of a and b. And then, of course, the integral will just be given by this, a log x minus alpha plus b log x minus beta. So that's how we deal with this first simple case. Let's look at a slightly more general case. And this is the case where the denominator is a product of distinct linear factors. So in this case, we're going to have n distinct linear factors, and we're always going to assume that the top is a polynomial of degree less than n. If the polynomial at the numerator is of degree greater than or equal to n, we have to do a little division, which we'll discuss at a later point. So, generalizing the previous procedure, we write the algebraic result says that we can express this in this form on the right-hand side as some constant over x minus alpha 1 plus a constant over x minus alpha 2, etc. So we set these things equal, we solve for these capital A's, these constants on the top, and then of course the integral is performed in the same way as before. It's just the sum of these simple log functions. Let's have a look at an example in the case where n is 3. So we have product of three linear functions on the bottom. What's an example of this? We're going to take 6x squared minus 7x minus 1 divided by x minus 1, x plus 1, x minus 2. So as I said, we write this as a over x minus 1 plus b over x plus 1 plus c over x minus 2. Again, we multiply through by the denominator on the left-hand side. And each time one of these terms cancels out with the thing that we're multiplying through by, leaving us with a, for instance, a times x plus 1, x minus 2, because the x minus 1 term cancels out with the x minus 1 on the bottom. And similarly for the other two terms. And on the left-hand side, we've multiplied through by the whole of the denominator, so we just get left with the numerator. To find a, b, and c, we follow the same kind of procedure as we did before. We choose values of x, which make two of the terms equal to 0. For instance, taking x equals 2 will make the first two terms 0 and give us an expression for c. Or setting x equal to 1 will make the last two terms equal to 0 and give us an expression for a. Here it'll give us 6 minus 7 minus 1 on the left-hand side, which is minus 2. And over here, it'll give us minus 2a. And so that tells us that a must be equal to 1. Then we set x equal to minus 1. That'll make the a term and the c term equal to 0. And on the left-hand side, this time we get 12. The b term becomes 6b. I'll leave you to do the calculations. So that gives us b equals 2. Finally, we set x equal to 2. And in this case, the first two terms are 0. And we end up with 9 on the left-hand side and 3c on the right-hand side. So c is equal to 3. So that gives us what we call a partial fraction decomposition for this rational function. And to find the integral of that function on the left, we just take logs. So it's log x minus 1 plus 2 log x plus 1 plus 3 log x minus 2 plus c. So that part is straightforward. The main challenge in the theory of partial fractions is actually doing this algebraic procedure. So we'll focus mostly on that. So this is how we do the case where the denominator is a product of distinct linear factors. Let's have a look at the case where the linear factors are repeated. In other words, that some of the linear factors occur to a power. Again, we'll do a simple example. Here's the general case. Let's look at this specific case where we have x plus 1 squared times 2x plus 3 on the bottom. So what happens in this case is we have to have a separate constant over x plus 1 and another different constant over x plus 1 squared. So kind of one of these terms for each power less than or equal to 2. If this was a 3, we'd have 3 such terms, etc. But let's go ahead and follow through and see if we can find A, B, and C. So our algebraic theorem says that there exist A, B, and C for which this is true. We just have to find them. Again, we start by multiplying through by the denominator. So here's the problem again. Multiply through, this time by x plus 1 squared, 2x plus 3. The denominator disappears on the left. Notice in this term, only one of the x plus 1's cancels out, so we get a times x plus 1, 2x plus 3. In the next term, both of the x plus 1's terms, as it were, cancel out, leaving us b times 2x plus 3. And in the last case, we get c times x plus 1 squared. Now we just have to solve for a, b, and c. We'll start by using the same procedure as before. Let's take x equal to minus 1 and see that the a and the c terms now are going to be 0. And if we calculate out the left-hand side, we get 1. And here the coefficient of b is also 1, so we have that b is equal to 1. Next, we want to make the 2x plus 3 term equal to 0. That we can do by taking x equal to minus 3 over 2. The calculation gets a little more complicated here, but it's simple arithmetic, so I won't say too much about it. The a and the b terms are 0, and once we do these calculations carefully, we see that c is equal to minus 5. So, now we don't have any more obvious choices of x, and we still have to work out what a is. But we can actually make any choice of x that helps us. I find that the easiest choice now is usually to take x equal to 0 and see what we get. Well, taking x equal to 0, we get 4 is equal to 3a plus 3b plus c. But we already know the values for b and c, so we can plug those in. So we get 3a plus 3 times 1 minus 5. And simplifying this and solving this algebraic equation easily gives us that a is equal to 2. So we end up with this partial fractions decomposition for the expression we started with. Now let's quickly talk about how to integrate this. It's a little bit more complicated. So we're looking for the integral of 2x plus 1 plus the integral of 1 over x plus 1 squared minus the integral of 5 over 2x plus 3. Well, if you're sophisticated, if you're confident about your integration skills, you'll see fairly easily that this is 2 log x plus 1 minus 1 over x plus 1 minus 5 over 2 log 2x plus 3. Now, if you're less comfortable with that, you can do these last two integrals using a substitution. In the first one, we'd substitute u equals x plus 1, and we'd end up with the integral of 1 over u squared, which is minus 1 over u. So that gives us minus 1 over x plus 1. And in the second case, we'd make the substitution u equals 2x plus 3. And this is where the 2 on the denominator comes in, because du is 2 dx. So dx is 1/2 du, and that introduces this half in here. So we get 5/2 log u, and then substituting back, we get 5/2 log 2x plus 3. So this is how to do the case where we have higher powers, repeated factors in the denominator. The next stage is to ask what happens when we have irreducible quadratics in the denominator, and this we'll discuss in the next video.